about the definition of QSR. What is QSR? That is, the physicochemical properties of any molecule is depend on its biological activity. We have also discussed the various types of parameters that are used in a QSR, evaluating QSR. And in previous lecture we have encountered only the names of their parameters, some of the parameters, that is lipophilicity, that is another electronic parameters, and different kind of parameters. So today in this lecture we will discuss about very descriptive, about each and every parameters that we discussed in the previous lecture. So today we will discuss about descriptors. What is descriptors? Descriptors are generally mathematically found, experimentally found, that links with the characterization of structure with the biological property. It is generally said that if some physicochemical properties depend on the parameters, then physicochemical properties, if some physicochemical properties depends on a particular descriptors, then biological activity parallels to the ordering of structure. Basically, we observe that in a thermodynamical system, that in a thermodynamical system, basically what happens, that entropy is generally increasing, and in case of when entropy increases, it occurs to be the attainment of randomness. So in biological activity, however, the ordering of structure is maintained. So it is basically a thermodynamical numbers. Descriptors are generally expresses such a property that biological activity is always parallel to the ordering of the structure. It is generally experimentally found property. So different types of parameters are different QSR parameters. Are, one is partition coefficient, another is constant, phi substitution constant. Third one, chromatographic substituent. Fourth one, solubility. Fifth one is elution time in HPLC. And the sixth one is parapod. So we have different symbols to represent these QSR parameters. Generally, the symbols, mathematical symbols that we generally utilize are for partition coefficient. We generally express it in the form of log P or log P square. For pi substitution constant, we generally use pi and pi square. Rn chromatographic substituent, we have the Rn log R. And for solubility, we have, for elution time in HPLC, we have log K, and for parapod it is. So we generally use these symbols to represent our QSR parameters. They are related to the structure of the compound and they directly relates to the biological activity. To some extent we will see later by giving some of the examples here. So another, we will discuss about each of these specific different other parameters also are present. Okay, electronic parameters. We have some of the experimental parameters, experimentally determined parameters. Experimental parameters. And there we have ionization constants. Ionization constant. Ionization constants. Then we have sigma substituent constant. Sigma substituent constant. Third one is spectroscopic chemical shift. Spectroscopic chemical shift. Resonance effect. Resonance effect. And another is field effect. Field effect. Then is ionization potential. The symbol we used in each of these cases is pKa for ionization constant, pKa and delta pKa. Sigma substituent constant, we can use delta plus, then delta minus, etc. For spectroscopic chemical shifts, we can use delta Fr or ppm. For resonance effect, we generally use R. For field effect, we generally use F. And for ionization potential, we generally use R. So these are the electronic parameters. Okay, for experimental parameters. For theoretical parameters, theoretical quantum mechanical indices. For theoretical quantum mechanical indices. We have atomic change densities. Atomic change charge densities. Atomic charge densities, we represent this as epsilon, and we have atomic net charge. Atomic net charge, we represent it as QT, Q delta. Super delocalizability. Super delocalizability. Here we are, SRE, and SRR. So these are the different electronic parameters. Okay. Now we will discuss about the static parameters. We have static parameters, and static parameters are related to the substituent group, the static hindrance, all these properties, because all these properties do influence the biological activity of a drug molecule. Okay. So we have static parameters. Static parameters. From here we will discuss Taft state constant. Taft state constant. It is generally represented as ES. Then we have van der Waals radius. Van der Waals radius. We generally represent it as gamma. Okay. We have interatomic distances. Interatomic distances. We represent it as P or L. P or L. And in case of molar reactivity as MR. Okay. So these are the various different levels of parameters that we use. One is electronic, another is the static parameters. Now we will discuss about what are the parameters actually. What we define as a parameters. So parameters can be divided into two sections. One is physical, another is chemical. Okay. It describes the chemical properties such as dipole moment. It also describes densities, electron donor and receptor pair, acceptor properties, electron donor, acceptor properties, and Hammett's electron constant, Hammett's electronic constant, and Taft parameter. Taft's parameter. In physical parameters, we generally deal with the skeleton, basic skeleton of the structure. Okay. So we here consider as water solubility, partition coefficient, then chromatographic RH value, RF value. RF means retention factor. Okay, that means the distance traveled by the solvent divided by the distance traveled by the solute. Okay, this is chromatographic RF values, and we have surface tension, and molecular weight. So we can describe parameters under physical and chemical section. Okay. Physical will always relate to the solubility, partition coefficient, chromatographic RF values, and surface tension, whereas chemical properties we will deal at the very basic core molecular level, properties that are intrinsic to the solute substance. Okay. What is dipole moment? Another is densities. Another is electron donor acceptor properties, Hammett electronic constant, and Taft parameters that we will later discuss on. Okay. So now we will describe about what are the various QSR methods. What are the various QSR methods? different QSR methods. So one method is by free energy model. Free energy model. Here we will discuss about the Wilson model, Wilson free energy model, and Hans model. Okay. Here we will discuss about Hans model, or it is also known as Hans free energy relationship. Second is free Wilson method. Free Wilson method. Okay. It is also a mathematical method. It is also a mathematical method. And another one is Martin and Kubinal method. Martin and Kubinal method. Martin and Kubinal method. Another is other statistical parameters. Second one is other statistical parameters. Other statistical method. Third one is pattern recognition. Pattern recognition. Fourth one is topological method. Topological methods. Fifth one is quantum mechanical method. Quantum mechanical. Sixth one is molecular modeling. So these are the different QSR methods. Now we will discuss about what are the different types of QSR that we are discussing. Listen, that QSR is a mathematical approach. It is a prediction about the properties of or the biological activities of a solid molecule, yet without synthesizing them. So we have to consider here that all these models that we will discuss here, they are just the prediction. They are the closer value, the result we will get from these mathematical methods is that we will just approximate that the value that we are arriving from any experimental procedures. Okay, we will get more close and close to that experimental value that we observed here. But it is not that exactly that it is a direct relationship with the actual actual biological properties, because it is just a predictive method. It is not much accurate. But we can, by using the parameters and by using different descriptors, we can understand that what a compound, an unknown compound should have to do with its biological response. The compound has its specific structure, it has its specific functional group, and we will able to predict without even synthesizing them that what we are approaching, towards what biological activities we are approaching. So this is actually the ideology of QSR modeling. Okay. Now we will discuss about what are the different types of QSR. So what are the different types? QSR types. So here we will understand about only QSAR Also, one type is 3D QSR, and the third one is hologram QSR. Nowadays, QSR have been replaced by the 3D QSR, because in 3D QSR we will have a structure prediction, that is the molecular feature, that is the extent through which substituent is placed within the three-dimensional space. Okay, so 3D QSR is nowadays more importantly focused. It is more focused. Only QSR is now obsolete nowadays. No one is really interested to run only QSR. And also, with this 3D QSR, this QSR is always conjugated with other spectroscopic method and other chromatographic method. In conjugation with the 3D QSR, they give more empirical results. That means they give more actual predictive results about the molecules. Such as when we perform 3D QSR, we generally associate it with LCMS. Okay, LCMS. That is liquid chromatography and mass spectroscopy. The association of all these different techniques of determining a compound, or you can say that the validation of a structure or a drug target, is to ensure that the molecule is correctly predicted. It is correctly predicted as a lead molecules. Otherwise, if we only perform 3D QSR, we will never be able to predict what the compound is. That means we cannot conclude the structure of the molecule only with the 3D QSR or only LCMS or only LC or only MS. We have to perform all these structures. Okay. So all these structures or all these techniques in conjugation with each other or in combination with each other gives a predictive result. So next we will discuss about the substituent constant. So we will talking about the different substituent constant. Now, substituent constant is basically that what is the effect of a particular group on a molecular structure. Generally, we will here discuss about what we call as a linear free energy model, or Gibbs free energy. That what happens when a drug generally interacts with its receptor. It displaces the water molecules that forms a layer over the receptor, and that disrupting of the ordered structure of water molecules, it brings about the change in the Gibbs energy, and that change in the Gibbs energy is proportional to the structure of the receptor. So in the next video we will discuss more details about the substituent constant. We will deal with some mathematical problems related to drugs. We will also discuss its additive properties and etc.